Hello everyone, welcome back to CSC webinar series of IIT Jodhpur. Today we have Dr. Angshuman Paul with us. He recently joined the department as an assistant professor, and his primary research interest is medical image processing, machine learning, and computer vision. Today he will be speaking about data efficient machine learning for the diagnosis of chest radiographs. Over to you, Dr. Angshuman. Dr. Angshuman, we can't hear you.
Am I audible?
Yes.
Okay.
Thank you.
Thanks for the introduction, Pallavi. And thank you also for inviting me as a speaker in this particular seminar. And I would like to thank everyone for joining this seminar. And before I start, please feel free to interrupt me if you have any question during the seminar. And if I am not audible somehow, please let me know. Let me share the screen. Is it visible?
Yes, yes, Angshuman.
So in this talk, I'm going to present some of our recent works on data efficient machine learning for the diagnosis of chest radiographs. So here is the outline of the talk. First, I would discuss what is data efficient machine learning, and then I would focus on why we need data efficient machine learning for medical images. And then I will discuss two of our recently designed methods. One is zero-shot learning for chest X-ray diagnosis, and the other one is few-shot learning using chest X-ray images from the published scientific literature. So at least for the first part of this talk, I would request you to interact, because I'm going to show you some images and going to ask you a couple of questions. So if you kindly interact, that would be very helpful. And I believe that would be helpful in clearing what I'm going to present as well. So the first question to all the audience is, have you seen an elephant shrew or a senji? Have you heard of this mammal? So this is particularly a mammal. The body of this mammal is similar to that of a rat, and the head of this mammal is somewhat similar, a miniature version of that of an anteater. So here is an image of a rat, and here is an image of an anteater. So this particular animal, Senji, has a head which is a miniature version of this type of head, and its body looks like a rat. Have you seen this animal ever? Has any one of you seen this animal? Any picture of this animal ever? If no one is answering, I am assuming that none of you have seen this animal. Now I am going to now please follow this description. These two descriptions. One is the body and other one is the head. Now I am going to show you some of the pictures. In left top, there is a picture. In left bottom, there is another picture of an animal. And on your right side, there is another picture of an animal. Now, can anyone of you tell me what is a senji? Out of these three pictures, which one is a senji or an elephant shrew?
Left bottom.
Left bottom. Anyone thinks anything else? Okay. So I'm assuming that most of you are thinking that the left bottom is a picture of the particular animal, elephant shrew or senji. Let's see. Yes. So you are correct. This is the animal senji or the elephant shrew. So what just you have done, that is called zero-shot learning. I guess those who have answered this question, answered in the speaker or have not answered in the speaker, but manually decided in your mind, you decided that this is the image of Senji. What you have done just is zero-shot learning. You have not seen this animal before, most probably, but I told you some description of this animal with the help of some well-known animals. And with that particular description, even without looking at any image of this particular animal, or without physically looking at this animal, you could identify this. So without having to look at any instance of this particular animal, you could actually identify the animal from a set of new animals, right? So this is precisely what we try in zero-shot learning. Now, why this zero-shot learning is important would be evident very shortly. Now, again, I am coming back to this picture. So I showed you three animals. The left bottom is Senji, the top one is Indian civet, and the right one is slow loris. Right? And now I am going to show you another picture. Can you tell me what is the name of this animal? If I say that this animal is one of the three animals that I just showed, can you tell me the name of this animal? Yeah, it's a slow loris, right? So this animal is a slow loris. You are correct. So what you just did is nothing but one-shot learning. If you had seen slow loris, that is a different thing. But I believe most of you have not seen this image of slow loris. I showed you only one image of slow loris, and you could, from that image, you could identify another instance of slow loris. So this, what your brain just did, is one-shot learning, right? And this falls under the category of few-shot learning when you learn from only one example. So our human brain has this unparalleled capacity of learning new concepts from only a few examples, only a few annotated examples, and even without having a single annotated example. So you just saw that zero-shot learning is possible where you did not need any image for understanding the new concept about the new animal. And you also saw that just by looking at one instance, you could learn about a new animal, right? So our human brain has this incredible capability of identifying new concepts from only a few examples. On the contrary, most of the modern machine learning approaches, especially the deep learning approaches, may require thousands, if not millions of data for understanding. And human brain can efficiently learn also visual appearances from their semantic description. So regarding the Senji, I just told you its semantic description that it looks like a rat, its body is like a rat, and its head is a miniature version of that of an anteater. From that semantic description, you could relate it to the visual appearance, right? But a machine finds it very difficult to relate the semantic description with the visual appearances. So data efficient machine learning is basically an attempt to bridge this gap in the capability of machine learning models to learn from only a few examples and also to learn without any annotated examples. Right? So in data efficient machine learning, we try to achieve the human level cognitive ability, although we have not been able to go to up that point, but we are trying to achieve human level cognitive ability. And this helps us in overcoming the curse of large annotation. Typical machine learning model, which require millions of data, also requires severe human effort to annotate those data sets. And to train such a model with such a huge data set requires a lot of time as well. If we can design data efficient machine learning method, that would not only be cost effective, but also faster as well. So data efficient machine learning is basically an attempt to mimic the human cognitive ability of learning from only a few annotated examples or no annotated examples at all. But why data efficient machine learning is so important in the context of medical images? So inherently, for medical images, some diseases are rare, for which getting annotated data or annotated images might be very difficult. If there is a rare disease and if you only have a few annotated image examples corresponding to that particular disease, and you want to train a modern machine learning method, most probably you will end up producing very low result, because modern methods require large number of examples. But if we can design data efficient models for rare disease diagnosis, those kind of models may be very useful. Also, in the context of medical images especially, an annotation requires the intervention of a human expert. Now, for the doctors to annotate images, it generally takes a lot of time. Annotating X-ray images might be easier, but annotating images like histopathology images or CT scans or MRI scans takes a lot of time even for a trained radiologist. And in scenarios like in India, because of the patient pressures, it may be very difficult to find time for the medical researchers and to annotate the data set, right? Therefore, if we need to annotate a large data set and that annotation has to be done by a doctor or a radiologist or a pathologist or an expert of that field, it might be very difficult to get that. So if we can reduce the burden of annotation, that would be less time consuming and that would be feasible for an expert as well. So that is why we need data efficient machine learning in the context of medical images. Now, I showed you two examples. One is of few shot learning and the other one is of zero shot learning. And these are the two of the most promising areas or avenues of data efficient machine learning. So in few shot learning and zero shot learning, researchers have started working for over last several years. And with the advent of deep learning approaches, these two fields have seen immense success. But most of the research in these two fields, in few shot learning and zero shot learning, are limited in terms of their application. They are limited to only natural images. Most of the tasks, most of the works that have been done in few shot learning and zero shot learning deals with natural images. There have been very few works in medical image analysis. So we designed some of the methods for few shot and zero shot learning with the chest X-ray images. And I'm going to describe a couple of those methods. Now, if we want to design a data efficient machine learning model for chest X-ray diagnosis, we face several challenges. First of all, we need to learn from a few examples or no examples, which is inherently difficult for the reason that I have mentioned. Another problem, which is evident in all the medical imaging modalities, especially in the radiology imaging modalities, is the noise. So whenever there is any medical or any radiology device and it scans human body, there is inherently noise due to the physics of the operation and due to many other factors. So this noise sometimes helps the radiologist for the diagnosis of certain diseases, but it sometimes hides the disease specific details as well. So if we try to design any machine learning model for radiology diagnosis, we need to deal with noise. But the problem of noise becomes more severe when we have only a few level data, which is the case in the context of data efficient machine learning. Now, also, it is sometimes very difficult to find disease specific features from the radiology scans. There are many reasons behind it. First of all, some lesions or some abnormalities are inherently of small size. Hello, is there any question?
And last year our revenue was there was approximately 65% of that revenue.
Ravindra, yeah. So someone by mistake unmuted.
Okay.
Yeah.
So Now, finding disease-specific features from the radiology images is inherently difficult because of several reasons. First of all, some diseases inherently causes small lesions or small abnormalities in the scans. So those as abnormalities, finding those abnormalities are sometimes difficult for even a trained radiologist. Now, in many occasions, different diseases may cause similar type of abnormality in the scans. Therefore, just by looking at the scan, you may not be able to find out what type of abnormality that is. One might require additional test, maybe a blood test or maybe some other kind of test to be sure about the type of the abnormality. So these are the difficulties associated with the radiology diagnosis. But this kind of difficulty are there in all sorts of radiology diagnosis, including data efficient radiology diagnosis as well. But this problem becomes more severe when we have only a few training data. So to overcome these challenges, we have designed a zero-shot chest X-ray diagnosis method using certain principles which helps us to deal with noise and other challenges. So in zero-shot diagnosis for medical images, we consider a couple of facts. First of all, there are some common diseases for which we can have a large pool of annotated training data. And there may be some rare diseases for which only a few or no annotated training data may be available. So our principle or our philosophy of the design was that we will use the annotated images of the common diseases. We will extract some meaningful information from that, and we will try to use those information for the identification of rare diseases or potentially rare diseases for which we might not have at all any training data or maybe only a few training data. Now, to be able to identify some rare diseases without any training data, we have to use auxiliary information. So in zero-shot learning, in a zero-shot learning setup, we divide all the diseases or conditions, or in general, all the classes into two categories. One is called the seen classes and the other one is called the unseen classes. For the chest X-ray diagnosis method, seen classes are some diseases and unseen classes can be thought of as some other diseases. For the seen classes, we have annotated images available during training. For the unseen classes, we do not have any annotated image available during training. So this is the difference between seen and unseen classes. But in some of the zero-shot learning setting, it is assumed that all the annotated training images might not be available. Unlabeled training images of unseen classes might be available during training, right? But for our experiment, we assume that for the unseen classes, we do not have any training data available, be it labeled or unlabeled. So in zero-shot learning, the training is done using the annotated images of the seen classes. And for testing, we might have images from both the seen classes and the unseen classes. So this setup is called a generalized zero-shot learning setup. Now, if we have only unseen classes during the testing, we call it a zero-shot learning setup. In our experiment, we used the generalized zero-shot learning setup where we could have both the seen classes and the unseen classes during the test. As I said, in zero-shot learning, auxiliary information plays a very important role. For the unseen classes and for the seen classes, in both of these cases, we assume that some kind of auxiliary information are available during the training of the model. Let's see what this auxiliary information is. In the context of identifying this elephant shrew, I told you that this is a mammal. Its body is similar to rat, and head is a miniature version of anteater. So this information are some kind of descriptive or semantic information about this particular animal, which helped us identifying the image of this particular animal. So this type of information, which is not exactly the image or which is not which does not belong to the modality that we are using for training and testing, This kind of information is called an auxiliary information. Many types of auxiliary information have been explored in the context of zero-shot learning, and we will see for chest X-ray diagnosis how we have used an auxiliary information. So the most obvious source for auxiliary information in radiology diagnosis and for chest X-ray diagnosis could be derived from the radiology reports. A report contains the description of a disease. Not exactly the description of the disease, but it contains some keywords or some description from which we can identify different diseases. So from these disease-specific characteristics described in the radiology reports, we try to design disease-specific signature. And these disease-specific signatures we design for both the seen and the unseen classes. Let's take an example. In the context of chest X-ray diagnosis, we divide the, let's say we consider pneumonia as a seen class and cardiomegaly as an unseen class. So during training, we will have disease signature corresponding to both pneumonia and cardiomegaly. Now, in our problem, we design disease-specific signature from the CT reports. So we use chest X-ray. Then why should we use CT reports for generating the disease-specific signature? This is because most of the diseases that we can diagnose from chest X-rays can also be diagnosed from CT. Therefore, a CT report may contain information that are related to the chest X-ray diagnosis, and because of the detailed content in the CT reports, it may be more informative compared to the chest X-ray report. Then we design a CT signature generator, which is nothing but a word-to-vec model called intelligent word embedding. And this model takes a CT report and generates signature corresponding to each of the disease or condition of our interest. For example, this SHI1 may be the signature corresponding to the disease pneumonia. SHI2 may be the signature corresponding to a disease pneumothorax. SHI4 could be a signature corresponding to a disease cardiomegaly. At this point, it is important to remember that the signatures are generated per class or per disease in our problem. It is not generated per data point. So the signatures that we get is for individual classes, not for individual data points. So overall, so far we have something like this. We have an input chest X-ray image, and we have some signatures generated from the CT reports, which creates the CT signature space or the semantic space, because it contains some kind of space constructed by this signature. We call it a semantic space. Now we have a chest X-ray image from which, by using some convolutional neural network model, we can generate some feature vector which will give us the visual description of this chest X-ray or visual features of this chest X-ray. Now we have these feature vectors and we have these signatures. How do we go about zero-shot learning? So for zero-shot learning, we need an embedding network. That embedding network will map the feature vector extracted from the chest X-ray to the CT semantic space. Let's assume that H is the projection of the feature vector obtained from this particular chest X-ray in the CT semantic space. Now we can easily see that SHI2 is the closest signature from H. Now if SHI2 is pneumonia, is the signature corresponding to pneumonia, then we can say that the input chest X-ray contains pneumonia. The disease or condition that is present in the input chest X-ray is pneumonia. That is how we can do using the embedding network. Now, since we are using chest X-ray as image input and CT reports for constructing the semantic space, we are basically performing an embedding from the X-ray space to the CT space. That is why we call it a cross-modality semantic embedding model. Now, to have a meaningful semantic embedding, we consider the following facts. Assume that for the given chest X-ray, we get the corresponding projection in the semantic space as H. Now, also assume that this particular image, we know that this particular image has a disease for which the signature is represented by SHI2. So we can easily understand intuitively that H should be close to psi2. If this particular image has to represent the particular disease represented by this psi2, H should be close to psi2. Therefore, the distance between psi2 and H, which is given by D, should be as small as possible. Also, the distances from the other signatures, psi1, psi5, psi3, and psi4, which are given by P, Q, R, and S, should be as large as possible. Therefore, considering this fact, we design a semantic embedding loss function, which is given by D minus summation of P, Q, R, and S. So this loss function, when we try to minimize, it tries to project the chest X-ray image closer to its target signature and projects away from the signatures that are not relevant to it. Also, another fact we consider in the semantic embedding, assume that these different colors represent the images corresponding to different diseases. Let's say each yellow point represent one image corresponding to cardiomegaly, each blue represent one image corresponding to pneumonia, and red represent pneumothorax. Then if we compute the centers of these individual clusters and the distances between the centers are V1, V2, and V3, then these distances should be as large as possible to have a good semantic separation. Therefore, based on this, we define a loss called semantic saliency loss, which is given by this formulation. It tries to, the minimization of this loss tries to maximize the intercluster distances computed between the cluster centers. So in this entire process pipeline, we have a feature extractor, which is designed using a dense net architecture and trained using only the scene classes. And we extract the feature vectors from the penultimate layer of the dense net. But these feature vectors can be noisy, especially because these feature vectors can be noisy, especially for the unseen images, because the model is trained using only the seen images. So the model does not have any information about the unseen classes. So at the test time, if we apply some unseen images to this particular dense-net model, the extracted feature vectors might be noisy. To deal with this noise, we design the embedding network in a suitable way. So to deal with noise, one way could be extracting salient features from the feature vector generated by the feature extractor. And extraction of salient feature can be performed well by an autoencoder. So an autoencoder takes an input X, create a hidden space representation Z, and reconstruct this X as the output X cap. And we map this hidden space of the autoencoder, or hidden state representation is of the autoencoder, as the semantic space or the CT signature space. So we design the autoencoder in a way such that when we apply X, the Z constructed in the hidden space represent the CT semantic space. So this is our projection network into the CT semantic space for an input image feature vector. So in the autoencoder architecture, we total have three loss. One is the semantic embedding loss, other one is the semantic saliency loss, and the third one is the reconstruction loss. And this autoencoder, we call it a semantic saliency preserving autoencoder. And we take an ensemble of such semantic saliency preserving autoencoder. It has been observed that ensembles are useful in dealing with noise. Therefore, we take a number of autoencoders that work in parallel and explore different feature spaces from the feature vector. So the feature vector that we extract using the DenseNet one-to-one model, we do not apply that feature vector as it is to individual autoencoder. Rather, we select specific subspaces from that feature vector to apply to individual autoencoders. So each autoencoder is trained in a slightly different way and learns different feature subspaces. So here is the overall pipeline. When you have a query chest X-ray image, you have a CNN-based feature extractor, which is DenseNet one-to-one. You get a feature vector. And then from this feature vector, you apply certain subspaces to individual autoencoders. And individual autoencoder performs a projection onto the CT semantic space. Now, based on this individual projection, each autoencoder assigns a class level to the input query image. for example, by this red autoencoder 1, the projection is closest to Psi2. So this particular autoencoder assigns class level 2 to the input data. Similarly, autoencoder 2 assigns class level 1 because it is closest to 1 for the input data. So each autoencoder assigns an individual a different class level to the same input data, and we do a weighted voting using the weights, using the quality of training of the autoencoders to find the final output class level. The weights are computed based on the quality of training of the each autoencoder. So this is how the input query image is mapped to the semantic space. And although we do not have any unseen class, unseen image during training, we can still get a class level corresponding to the input data based on the signatures of the individual diseases. See, these signatures can belong to seen classes or can belong to unseen classes. As we said, that we assume that signatures for the seen and the unseen classes are available. Based on the projection close to a particular signature, individual classes are assigned, and based on the voting, we can find the output class level. So although we do not have unseen class annotated data of unseen classes, we can still find out whether an input query image belongs to seen class or an unseen class. We perform our experiments on 3 datasets: NIH dataset, NIH 900 dataset, which is a hand level subset, and the OpenEye dataset.
Sir, can I ask a question?
Yes.
If you please go to the previous slide. Here, how come the 4 different autoencoders will map to 4 different groups?
Because each individual autoencoder is trained differently because of choice of the individual subspaces. So there is a strategy called bootstrap sample by which you can choose different data for training individual autoencoders which are trained in parallel. And then suppose you have a d-dimensional feature vector, and from that you choose d prime dimensional feature subspaces. With individual subspaces, you train individual autoencoders. So each autoencoder is not trained similarly. As a result, their weights are different. And as a result, when they map the same feature vector, the individual subspaces of the same feature vector, they perform different mapping to the same semantic space.
Sure, thank you.
So the performance measure for zero-shot learning is generally some kind of performance metric on the seen classes, performance metric on the unseen classes, and a harmonic mean of the 2 performance metrics. We consider recall values at the performance metrics. So we compute seen recall, unseen recall, and the harmonic mean of the 2 recall values. And the harmonic mean is the most important one in the context of generalized zero-shot learning because it takes into account both the seen and the unseen recall values. So for our experiment, we divide we consider 9 diseases and conditions that can be diagnosed from the chest X-rays, and we divide these into 6 seen classes and 3 unseen classes. This division was random. And you can see pneumonia, nodule, pneumothorax, consolidation, effusion, infiltration, these are seen classes, and edema, emphysema, cardiomegaly, these are unseen classes. Now we have computed the harmonic mean of the recall values for different data sets using our method and using other 3 methods. So these are some of the methods, GMN and GRAN, that are applied on natural images. So we just use this model for to see their performances on medical images. And SAE is the semantic autoencoder that is a variant of the autoencoder itself used for this particular model, this particular problem. And we can see that compared to these methods, our methods show superior performance in terms of the harmonic mean of the recall values. Although you can see that the performance for unseen, because of the low performance of the unseen classes, our accuracies are very low. But also it is to be remembered that this is the very first attempt on designing some zero-shot learning methods. So these are some of the recall values for different diseases and conditions in the different data sets. you can see that for some diseases and conditions, we have good recall values like 56%, 40%, etc. But for most of the diseases and conditions, we have very low recall values. So this is what we have obtained is through our experiments. And here are some visual results. So in chest X-rays with seen classes and unseen classes, we can see that for some images, we are able to find out the correct class. So GT represents the ground truth class and D is the detected class. If the detected class matches with one of the ground truth classes, we consider that to be a true positive detection. Now, in case of unseen classes, the number of true positive detections are less compared to the seen classes in general because that information was not seen during training. And one point has to be remembered here in the chest X-ray dataset, we have most of the chest X-ray images with multiple classes, and our method can detect only one class. Therefore, our method is not a multi-level detection method, but it can detect one of the possible classes that is present in the chest X-ray. So we have also performed some ablation studies with single autoencoder without considering the autoencoder ensemble and random subspace selection. So we had selected the subspace in a semi-deterministic way. Instead of doing that, we have done random subspace selection. And by doing that, we have repeated these experiments on the different data sets. And we find that in terms of the harmonic mean of the recall values, in two of the three data sets, our method is found to have superior performance compared to the other two variants. This is a very important observation in terms of the signatures. So we had generated some signatures using the intelligent word embedding method. Now, instead of generating that signature, if you just use a random signature, a random vector that represents a signature, how do our method perform? You can see in the harmonic, in the seen classes, even using junk signature or arbitrarily generated signature, you can get better result compared to our method. But when it comes to the unseen classes, always the signatures generated using the intelligent word embedding method perform superior. This is a very important observation because it shows that with arbitrary signatures, you can perform semantic embedding, and that might be good as well, right? But when you try to generalize it to the unseen classes, which has not been seen during the training, then the problem comes. You don't get very good results. Right. So that is the importance of signature generation in an appropriate way.
Sir,
So
here
that's
actually, sir, here actually what actually signature represents.
right.
We
So,
have a chest X-ray and we are converting it to signature. What it contains, a numerical value or a feature.
right.
What
So
actually it contains represents.
right. Signature value represent a numerical feature, a numerical vector corresponding to each disease. So if you consider word to vec model, if you input a word, it will produce a vector representing the semantic presentation of that particular word. The signature is nothing but that. If you apply pneumonia, if you apply the word pneumonia in that model, it will generate a vector. The vector might be 0.5, 0.3, 0.7, something like that.
Okay, so we are taking the chest X-ray images, that means the vision, and we are
I'm sorry, I cannot hear you. Sorry, I did not get your last part of your question. Can you repeat that?
Similarly, we have word images. Are you able to hear, sir?
Can you repeat that once more?
So actually, what we are doing is we have an image. So from image we are computing features, and similarly from the description of the diseases like pneumonia, etc., we are computing the embeddings. So word embeddings, text based upon the text, based upon the image, we both combining to achieve zero shot and one shot learning.
Right. Zero shot learning, not one shot, zero shot learning.
Yes.
Yes.
Thank you, sir. Thank you.
So as we just discussed, we are using auxiliary information from the radiology reports, especially from the CT reports. So the question is, can we use more auxiliary information? The answer is yes. Actually, we had tried to use different types of auxiliary information. We have done some more experiments in some other works where we have used auxiliary information from the X-ray report as well, alongside the auxiliary information from the CT reports. We have also used some human specified traits, such as the position of the abnormality, the size of the abnormality, the opacity seen in the abnormality. And we have seen that that kind of auxiliary information also helps us to improve the results of zero shot learning. And with the use of those kind of information, we have been able to improve the overall quality of the zero shot learning. So that's about the zero shot learning. And now I'll briefly show one more work where we have tried to design a few shot learning model using the images from the published scientific literature. So this was a very ambitious project in which we tried to mimic the learning process of a radiologist. So a trained radiologist knows the description of many diseases. Now suppose a new disease comes in, and there is a say for example there is a journal that describes that new disease with a few images or few radiology images of that disease. The trained radiologist should be able to read the article, and sometimes the radiologist learns to identify that particular disease by reading the article. So this is something that largely happened probably during COVID also. When COVID came, the initial reports or the initial articles that came up in the journal, the radiologist read it across the world and identified how a COVID patient presents or how the scans look like. And this is often the radiologist or any other field expert do by reading the journal papers, by looking at the images, they try to learn. And they use their previous learned concepts in this new learning. So we tried to mimic this exactly same learning process in our few shot learning framework, but we tried to design a method from the published scientific literature. So the problem in the images in the published scientific literature is that these images may be of lower resolution. These images may be of arbitrary sizes and may contain arbitrary artifacts. For example, you can see in this chest X-ray image, there are some arrows, right? And these arrows may make it difficult to identify the disease-specific information from the image. There may be many other types of markings and annotations in these images, which makes it difficult. And the images might be of low resolution. So what I precisely want to say is that the images published in the scientific literature are very different from the images that we get in the standard clinical procedures or standard clinical X-rays. So we tried to use the images from the published scientific literature alongside some images from the standard clinical procedure to design a few shot learning method. We obtained the label images from the PubMed Central, which contains a collection of different articles, and that helps in the initial training of the few shot learning model. And then we took some unlabeled clinical images from the NIH chest X-ray dataset, which are high resolution and less artifacts. And with the help of these unlabeled images, we performed a retraining of the model, which helps us to get rid of the noisy labels and helps to improve the performance of the model. So here is the entire process pipeline is basically the same philosophy. We have an autoencoder as the classifier. We have a feature extractor. We generate a feature vector, and this autoencoder predicts the level. We don't use an ensemble here. A single autoencoder predicts the level. Now, in the initial phase of the training, we have some training images from PubMed Central, which are the images from the published scientific literature. There is a feature extractor, which is designed by DenseNet. It extracts feature vector. And then with the help of this feature vector, we train this classifier. The loss function for this classifier is the autoencoder reconstruction loss, standard reconstruction loss that I have already described. And there are some other loss functions also that is computed from the cluster, just like the previous one. Suppose we have the training data X, which is reconstructed as X cap. And in between the hidden state comes this kind of cluster. So here we change the philosophy slightly while considering the cluster. So these data points inside a cluster should be as close as possible. So Dij, if that measures the distance between two data points inside a cluster, should be as low as possible. And the distances between the cluster centers are AB, which was represented, which is similar to the previous one where we used V. These RAB should be as large as possible. Based on these, we designed two loss components corresponding to each cluster. One which we called condensation loss, which tries to minimize these Dijs for each pair of points inside a cluster. And the other one tries to maximize RAB, the intercluster distances between a pair of clusters, between every pair of clusters. So altogether, we have three losses here as well: reconstruction loss, condensation loss, and the separation loss. We get an overall loss function considering these three loss components, and by minimizing this loss function, we train the autoencoder. So once the initial training of the autoencoder is done using the PubMed central images, we take some high resolution but unlabeled images from the NIH chest X-ray dataset, which are clinical chest X-ray. Now, we apply these images to the classifier and we predict the level by this classifier. This is called a pseudo level. With the help of these pseudo levels, we then retrain the classifier. So classifier predicts the pseudo level for the unlabeled images, and then with the help of the pseudo levels, we retrain the classifier. So after retraining, the retrained classifier is used for inference, where we apply a query chest X-ray image, and it predicts the level corresponding to this chest X-ray.
Sir,
Here, yes.
Sir, one doubt, sir. In the previous slide, here
Yes.
the predicted label autoencoder will this give us a representation. The middle give us the deep representation, which we
Right.
use it for predicting the label. Sir, autoencoder won't give any label. We process and come up with.
Right. So autoencoder will not give any label directly, but as I showed, let me go to the slide. As I showed here, you can just measure the distance from the closest cluster center maybe. So here I am showing signature, but instead of that, you can consider the closest cluster center, and you can assign based on the cluster center, you can assign the label to this particular query point.
Sure.
So autoencoder, you're right. The autoencoder by default will not give a label. We modify the autoencoder with the class levels to give us a label.
Yes, sir.
So, right. So after retraining, we predict the labels for the query image. And in the few shot learning framework, here we consider 14 diseases, and one condition called no finding, which is basically the normal chest X-ray images. And we divide 12 out of these 15 classes. We consider 12 classes as base classes, for which we assume that we have large amount of training data. And the rest three classes, cardiomegaly, emphysema, and edema, we consider these three classes as novel classes, for which we assume that we have only a few training data. Now, the feature extractor in our framework is trained with the base classes, and the classifier is trained with the novel classes. And the performance of the few shot learning method is evaluated on the novel classes. So as I said, the initial training of the model is performed using the images from the PubMed Central Open Access dataset, some images from the PubMed Central Open Access dataset. Retraining is performed on the NIH training dataset, and test is performed on the NIH test dataset. And the target abnormalities of the novel classes are cardiomegaly, emphysema, and edema. So this is the overall F1 score and the area under the ROC curve for these three particular diseases or conditions. And these are some of the existing methods for few shot learning. And we find that in the proposed method, in most cases, we obtain the best AUROC and the best F1 score for different diseases. Only except for the cardiomegaly, where prototypical network gets the best result. So these are some of the image examples. The left two images, for the left two images, we find the right class level. For the rightmost image, we cannot find the right class level. So this is an inaccurate detection. So we have also performed some ablation studies to look into the impact of retraining and the different loss components of the autoencoder. So WRT is basically without retraining, the performance without retraining. And in most cases, you will see that at least in 2 out of the 3 cases, without retraining, we get significantly lower performance compared to the proposed method. And AERE, basically the autoencoder with only the reconstruction loss without considering the other losses. And you will see that in most cases, AERE also obtains inferior result compared to the proposed method. Thus, it signifies the importance of individual components of the framework. So I had planned to discuss this method as well, but I think I don't have much time left. Pallavi, how much time do I have?
Maybe 5 more minutes.
Yeah, I think it might be difficult to discuss that. So probably I would go to the questions. If you have any questions, you may ask. Yes.
What slide you can explain, sir? In this two, which is the text of the framework.
I'm sorry, I am having difficulty to hear you. I don't know whether this is the problem of my internet from your side.
Sir, you can explain one slide which contains architecture from these two methods. Two slides.
Architecture. This one.
No, sir, the next slide which you want to discuss two papers on few shot which you displayed.
Oh, okay. So this architecture is not significantly different. This also has this autoencoder ensemble. So this is the overall pipeline, but here the difference is that we used all the clinical images, not images from the PubMed Center, not images from the chest X-ray, not images from the published scientific literature. And here we have done the experiment on a large number of combinations of base and novel classes. So that's the major. So this is the overall process pipeline for the diagnosis, which is similar to what we had done earlier. But here we have done the experiments on the clinical quality chest X-ray images. And the significant difference here is that we do not need any retraining here, which we needed earlier. Here we do not need any retraining here. And so this is probably the most important part. Here we have used different combinations of base and novel classes. Actually, exhaustively, we have used combinations of base and novel classes. Every time we had chosen 3 novel classes, and rest of the 12 have been treated as base classes. And these are, so in the 2 data sets, we have performed the experiments with a number of different methods. So these are some of the results in the OpenEye data set. And these are some of the results on the NIH chest X-ray data set. So we have also performed some ablation studies on the OpenEye and the NIH chest X-ray data set to look into the individual components of the proposed method. And generally, our method is found to be superior, including all the components, if instead of excluding certain components. So, but one point has to be remembered in the context of all of these methods, that the training of most of this method. So we have shown the results on the OpenEye dataset, in some cases NIH, in the training using the NIH dataset, and shown the results on the OpenEye dataset. For example, here we have not used any training data from the OpenEye dataset. We have trained using only the NIH dataset and tested on the OpenEye dataset as it is. So the results here also show the generalizability of the proposed method across datasets from different sources. So here is the conclusions. We have proposed 2 methods, several methods for zero shot and few shot diagnosis of chest X-rays. The zero-shot learning method relies on the signatures from the CT radiology reports, and we have seen of late that signatures from other sources might also be useful, such as the trains. And in case of few-shot learning, we have used images from the published scientific literature. We have also designed a method for learning only from clinical chest X-ray images. And in our method in learning from published scientific literature, we have tried to mimic the learning of a radiologist. And retraining with pseudo levels has proved to be useful in the context of few-shot learning. And these methods, if we can improve the results further, can be useful for the diagnosis of rare diseases. So that's very much it. If you have any more questions, you can ask.
Is there any question from the participants? Okay. I guess there is no more questions. Thank you so much, Dr. Angshuman, for such a wonderful talk, and thank you for kindly accepting the invitation.
I think somebody.
There is a yes. Yeah, Chandrasekhar. There's something in the chat.
Can you read the question? Oh, there are a few questions. Can you read the question for me?
Yeah,
because
yeah.
I am having difficulty in finding the chat.
No problem. So from Chandrasekhar, there's a question: the reason to choose AE. Oh, that's
Okay.
all.
Okay, so the reason to choose AE is that AE can extract salient features. And as I said, that from the visually, to do a few-shot learning or zero-shot learning, you need visually discriminated features. The feature extractor the feature that is extracted by the feature extractor might contain some noisy features as well. From that, you have to find the salient feature representing a particular disease. That is why we choose AE. AE autoencoder is useful in extracting salient features.
Sir, we are using autoencoder to reduce. Means the feature extraction is completely we are focusing on autoencoder. So why not any other CNN or PCA techniques? Because the whole autoencoder is for reducing dimensionality and extracting the feature. So why not other networks like CNN or PCA, Siamese network?
Right. So it's just not dimensionality reduction. Autoencoder is not only intended for dimensionality reduction. It's also for extracting salient. So in autoencoder, we have the flexibility, as I shown in this slide. We have the flexibility of considering the reconstruction loss, and we can also incorporate some cluster-based properties into the representation of the hidden step. And forcing those cluster-based properties to be satisfied during the training of the autoencoder, we can expect to have better salient feature extraction from the input feature vectors. That is why we use autoencoder. We can, of course, try with PCA or other unsupervised or supervised approaches. That might also work well. We have not explored that, but that can also work well. I'm not saying that that will not work, but this is the philosophy that for which we adopted the autoencoder.
Thank you, sir. Thanks a lot. One of the best presentation I have attended. Thanks, sir.
Thank you.
So there's one more question. What are the challenges that you face on your proposed method?
Right. So many challenges. The first obvious challenge is that we don't get very good results, right? So, and that is something we expected, to be honest, because whereas an ImageNet trained model uses millions of level data, we are using only 5 level data in few-shot learning, and in zero-shot learning, we are not using any level data from the answer classes. We are only relying on the auxiliary information. So we are not getting good result. And as I said, that is something we had expected. But that's not the end of it. We are trying to improve it by incorporating more and more information, by trying to improve the methods. So, so that is one of the challenges. The second challenge is that disease-specific characteristic. So if you look at the chest X-ray images corresponding to different diseases and conditions, many diseases have got similar appearances, and that creates a problem. So if human being cannot differentiate between a disease, we generally cannot expect a machine to differentiate between them. So whatever feature they extract might be confusing, might be difficult to differentiate. And there are problems of nomenclature as well. So for example, in the NIE chest X-ray dataset, there are some. It uses some names like. So I can show it here. So if you look at this set of diseases, we have some names like infiltration, which in many parts of the world, this name is obsolete. Radiologists don't use this. They categorize infiltration in the same category as, sometimes same category as pneumonia, right? So if we want to generalize it across the datasets from other sources, we might face a difficulty in terms of the labels. So that is actually a difficulty when we try to generalize across the datasets from different sources. On top of that, there are problems of noise, and for the PubMed central images, there are problems of resolution. So these are the main challenges that we face.
Dr. Paul? Yes. Sir, if time permits, I have one question.
Yes.
Suppose, sir, if there is a user, assume that it is a signature classification. Suppose signature means for a user, we have a set of genuine signatures and a set of forgery signatures. Okay. Now, if I want to train the model for one-shot learning, so if I take one sample from each user, I will take one sample representing genuine signature and one sample representing forgery signature for all the users. So is it called one-shot learning, or do I need to take only one sample, either forgery or genuine, and use it for training? So which is one-shot learning here?
Right. So good question. It's a bit subjective in your context. So if you take one signature per user, well, because a signature, so depending on, so see, the concept of one-shot learning or the zero-shot learning is defined based on how you define the classes, right? So essentially, the definition is in one-shot learning, you have only one data point from a class, right? From a class. So from a class, from cardiomegaly or from pneumonia, for example. So if you consider a user to be a class, then your problem is one-shot learning. If you consider the two classes to be forged signature and the original signature, then your problem is definitely not one-shot learning.
Yes, sir. Suppose my aim is classification, not the user. I want to tell whether it's a genuine or a forgery.
I would say it's not one shot. Because your classes are genuine and forged, right?
So from each user taking one sample of genuine, one sample of forgery, doesn't call that one shot?
I would not call it one shot. Somebody else might call it, and we can have a long argument regarding that as well. But I would not call it one shot because your classes are genuine and forged. So I will not call it one shot.
Okay.
Dr. Paul, am I audible?
Yes. Yes, yes.
Doctor, I'm not from computer science, so my question is very generic in nature. So is there any application beyond medical imaging of your approach?
Oh, yes, definitely. I mean, a lot of applications. Like, for example, in economics, when you have, let's say, when you there is a sudden change in the market scenario, for example, and you have only a few data corresponding to that. When the market crashes for a particular reason, for example, you have only a few data corresponding to that. And then maybe you need to immediately forecast the stock prices in such a situation with the help of only a few data. Because the significant crashes in the market don't happen every day or every month, right? So you have only a few data. So few shot learning can be applied. Few shot learning can be applied in other scenarios such as navigation. So in navigation, you sometimes face problems where so Google Map actually tells us the road which we need to follow for reaching the destination in the fastest manner. Now, suddenly, let's say there is an accident or there is a roadblock for some reason. Immediately, based on that, you have to reroute the car, right? So Google Map has to reroute the car. And Google Map don't have a lot of information of that particular road. Every day, that kind of accident or road blockage does not happen. So based on that, based on only a few information or only a few additional information, it has to find the best possible alternative route. there also you can use few shot learning. And in many other cases, in astrophysics, in particle physics, in agriculture, in weather forecasting, in many other applications, you can use few shot learning.
Thank you.
Thank you, Dr. Angshuman. I guess there's no more questions. Thank you for joining us. Thanks to all the participants. Have a good evening.
Thank you so much.
Bye-bye.
Thank you, sir.
Bye-bye.
Thank you. Thanks for loving.